Hi everyone. In this video, we're going to be talking about the transport analogies as it relates to the transport of thermal energy. The analogies for electric charge, mass, and momentum transfer videos are all available in the description below if you're interested. The purpose of these analogies are to demonstrate how electric charge, mass, heat, and momentum transfer are all mathematically analogous. By that, I mean that the transfer of all these properties act according to a general rate equation. So the rate that something occurs is the driving force over the resistance against it. Really think about this though. Think of the driving force like the amount of water flowing out of this pipe here. With little to no resistance, it seems almost obvious that the water will come out of the outlet at a high flow rate. However, if we place some resistances in the pipe, like more pipe friction along the pipe's edges, we will greatly decrease the rate at which the water comes out of the pipe. So let's get back to our heat transfer analogy. Let's assume that we have this solid rectangular piece of metal here. Initially, the whole piece of metal is at 15 degrees Celsius. Then, let's say instantly, one of our outer faces is heated to 50 degrees Celsius. What do you think is going to happen? Well, the thermal energy from that heated face will begin to heat up the rest of our metal block at a certain rate. A rate that can be found using the transport analogy that we described previously. So, what will our driving force be in this example? Well, in this case, it is going to be the temperature gradient. If our side was heated to 100 degrees instead of 50 degrees, it seems almost obvious that the bar will heat up much quicker, right? But what about our resistance term? Well, the resistance here is going to be 1 over the conductivity of the metal. And as a reminder here, the conductivity of a material describes how well the material can transfer thermal energy. So, a material with a high thermal conductivity will transfer the energy across our block at a very high rate because of the little resistance. Whereas if we had a material like wood, for example, we will have a low rate of thermal energy transfer, as woods often generally have a high resistance to thermal energy transfer because they have a low thermal conductivity. So now that we understand what our driving force and resistance to the rate of heat transfer are, let's take a look at how we can better understand the rate of thermal energy transfer. Let's begin with the driving force, which, as I previously stated, is a temperature gradient across the block of metal. Let's begin simply by assuming a one-dimensional heat transfer problem. So, the temperature gradient can be expressed as the change in the temperature over the change in our x direction. Now, what about our resistance term? Well, the resistance term can be stated as R, which is simply 1 over the conductivity of our material. And let's just simplify this by bringing the conductivity term to the front of our equation. So, applying these two terms to our transport analogy, we get Fourier's first law of heat conduction. So, what this is saying is that the heat flux, the amount of heat transferred per meter squared, is equal to the temperature gradient across the material times the conductivity of that material. To build on this, as long as our materials are isotropic, which just means that the transfer of heat is equal in all of its directions, we can expand the Fourier's heat conduction equation and write it as a vector equation, which this nabla or del term here just represents the gradient of the temperature in all spatial directions. Thank you for checking out this video, and I hope it helped your understanding about how the transport analogy relates to heat transfer. If you enjoyed, please like and subscribe to support the channel. However, if you have any comments, questions, or concerns about the information I provided in this video, please leave a comment down below and I will do my best to address your concerns.